Hi. Today we are going to talk about how we can use a simple tool like Excel to try and optimize the mass distribution in a two-stage rocket. So this is a pretty simple toy problem, but it explains most of the things which go into designing a launch vehicle. Most of the intricacies about choosing the mass ratios, the structures ratios, and things like that. So just to illustrate that, I have picked up a problem from a book. The problem says a two-stage rocket is to be used to put a payload of 1000 kg into low Earth orbit. The vehicle will be launched from Kennedy Space Center, where the speed of rotation of the Earth is 427 meters per second. Of course, if it's done, the thing is launched from Sriperumbudur, it will be slightly different. It depends on the latitude where it is being launched. Also, the problem says assume the gravitational velocity losses to about 1200 meters per second and aerodynamic losses with respect to 500 meters per second. The first stage it burns kerosene and oxygen, a storable liquid propellant rocket, with a mean specific impulse of 320 seconds average over the flight time. While the upper stage burns a cryogenic hydrogen oxygen with an average specific impulse of 450 seconds. The structural coefficient of the first stage is about 5%, meaning that the structure weighs about 5% of the total propellant weight. When I say structure, it's not only the structure, it's the electronics, the nozzle, all other things which are used to fabricate a stage. 5% is pretty low, but as I said, now this is an illustrative problem. We can change that when we want it later. The second stage being a cryogenic stage, the tankage and other things are heavier, so that will be around 7%. So the basic idea is determine the payload ratios and the total mass of the vehicle. Okay, so this is the problem. If I have to launch a 1000 kg satellite into a low Earth orbit, so now let's find out what is the velocity needed to put it into that orbit. Okay, the first point we need to look at is the delta V for low Earth orbit is about 8 kilometers per second or 8000 meters per second. But you have to add to that the gravitational loss, that's about 1200 meters given in the problem. Drag loss 500 meters, these are the ones you have to add. But you can take advantage of the rotational speed of 427 meters. So if you total up all this, 8 kilometers plus 1.2 kilometers plus half kilometers minus 427 meters, you get a delta V of around 9273. Okay, so this is what is the thing. So what we do for this calculation, we need to set up the stages. And for that, I just set up here, and I'm going to start with 1000 kg as initial guess. Of course, you will not get the kind of velocity increment you need, but this is just to start the calculation, as I'll show you a little later. So the first stage, m prop, is the mass of the propellant in the first stage is 1000 kgs. The structure ratio is given as 5%, so that will be mass of the structure will be 50 kgs. ISP is given as 320 seconds. Now the initial mass of the first stage, this is a little tricky. We have to be careful while doing this. So that's why I've highlighted this in green and explained here. Initial mass of the first stage is mass of the payload, mass of the propellant of the first stage, structure mass of the first stage, plus the mass of the entire second stage, that is mass of the propellant of the second stage and the structure of the second stage. Okay, and that adds up to 3120. Basically, it's 1000 from the payload, 1000 from the propellant here, 50,000 and 70 here, so it adds up to 3120 kgs. The M final, everything else will be there except this 1000 kgs of the first stage propellant will be burned, so that will be 2120. Okay, and we all know the equation to estimate the delta V, which is imparted by this stage, is gravitational constant g into ISP, that is 320, into logarithmic ratio of the initial mass to final mass. So plugging that here, that simple formula, you will get a delta V of 1213 meters per second. That is, if the first stage propellant is only 1000 kgs, this is what you will get. Okay, similarly for second stage, mass of the propellant, again, as I said, starting I have said 1000. Structure ratio is 7%, so that will be 70 kgs added to that. ISP in this case is higher, 450. Now, in the initial mass of this, again, I need needs a little bit of explanation. That's what I've done here. This, of course, still has the payload, structure mass of the first stage, propellant mass of the second stage, and structure mass of the second stage. Okay, so this is what it will be. In this case, of course, you have to also jettison the structure mass. So in this case, I'll just make a small correction here. So that will add up to about 2070. 1000 for the payload, 1000 for the propellant, and 70 for the structure. ISP is 450 seconds. Again, plugging in that formula delta V is equal to G into ISP to logarithmic ratio between final initial and final mass, you will get a delta V of 2913 meters per second. Okay, so this if you add up both the velocities from whatever you got from first stage and second stage, that you get only about 4,126 meters per second. That still leaves us a deficit of 5,146 because what you really need is 9,273. So how do I try and get the required velocity? One thing I can do is I can arbitrarily change the mass of the first stage propellant or mass of the second stage propellant. I can keep on doing that and try and error method. But instead, I can use a very simple tool which is there in Excel. So which is what I will do. So it will let the Excel do the work. So here I go to tab data. And then one of the things is called what if analysis. This is used largely by business people, but I don't see why we can't use it here in this case. So in that what if analysis, there's something called goal seek. What is the goal I want to seek? In this goal, I want to seek is the difference between whatever velocity I calculate and whatever is required should be 0, meaning that I should get exactly the same. So what I have done, I have defined another variable called deficit here, which is simply the difference between required velocity and obtained velocity based on this calculation. So what I do here, I go and say select cell which I want to make. So I'll take this deficit cell as the one I want to do. I want it to be 0, but since 0 can cause some problem, I'll just make it a small number, something like, let's say, 1 meter per second. By changing what? By changing this mass of the first stage propellant. And then I say OK, and you'll see it runs very quickly. And it says if the first stage propellant mass is 20,304 kgs, with the same structure ratio of 5%, now the structure becomes 1,015 kgs. As you can see, the second stage is untouched as it is. So now I have achieved the delta V required at 9,272 meters per second, but the total mass of the system is now 23,389 kgs. So this is the gross mass of the launch vehicle. This is one option I can do. Now the question is, why should I change the first stage? Why not freeze the first stage and change the second stage? Because that seems to be higher energy. So we just cancel here. Again, I'll go back to the same what if analysis, goal seek. And as before, I'm going to set this value to 1, that is deficit to 1, to value 1. You can, of course, put it even as 0.5, doesn't matter really. And then I'm going to say, instead of mass of the first propellant, first stage mass propellant, change the mass of the second stage propellant mass of the second stage. So you run that. So what you get, it's a slightly different answer. You will be surprised. There is a significant difference now between the initial gross mass and the final gross mass. Now you see what was about 23,000 odd gross mass is now reduced to 15,940. So now the launch vehicle is lighter if I change the propellant mass the second stage. So this is an interesting observation. Now what I can do is, why not change both of them at the same time? Let the system change both mass of the propellant 1 and first stage propellant and second stage propellant together. Unfortunately, that cannot be done by goal seek. However, there is another option which we can do. So what we can do here, there is a plugin called Solver. So I take the Solver plugin that comes in here. There again, as I said, set objective, this is deficit to a value of 1 by changing. In this case, if you see, let me zoom it a bit. It doesn't seem to zoom well. So anyway, if I zoom here, obviously this is there, apparently it cannot zoom, but it doesn't matter. So what I am saying here is I am going to change the mass of the first stage, propellant mass of the first stage and propellant mass of the second stage simultaneously. Okay, and I am going to say constraint. What will be the constraint? Constraint will be this. This. I have to add a constraint. A constraint will be the delta V I require will be equal to this value. Okay, so I have added that constraint. That constraint is added. Now I can say, okay, do solve. If I press solve, okay, there is a problem here. Let me cancel that. Maybe this is not required. Okay, let's see if it works without that. Content. Maybe I picked the wrong cell. Okay, hold on. That was the problem. Okay, now we should be able to solve. So solver has found a solution which says that the first propellant mass of the first stage is 5,300 watt, second stage propellant is 7,500 watt, and I get, of course, the velocity I need, the delta V 9,272. And now the total mass, as you can see, is even less than when I change the second stage, about 14,622. Okay, so now let's summarize the stuff. I can say keep this here, and then if you go to summary, three things we tried. We first changed the mass of the propellant mass of the first stage. That gave us a total mass of the launch vehicle as 23,389 kgs. Then we froze the first stage and changed the propellant mass of the second stage. Then we got a total gross mass of 15,940, a very significant reduction from that. So when we change both at the same time, we get even less, 14,622. So the point of using this exercise is to show you that even with Excel, which is easily available in all these systems, we can do some studies to try and understand the importance of each stage and mass of each stage and all that. Of course, in this case, we have also the freedom to change the structure mass, structure ratios from 50 to 70%. We can change that. We can also change, fool around with ISPs. Put the more high energy one on the first stage and the second stage differently. So all that things we can do, quite a bit of exercises we can do with this simple tool and with very, very quick things. Of course, in real scenario, when they want to design a launch vehicle like the PSLV or GSLV, they have to go into much more complex optimization routines. And the usual optimization techniques use Lagrange multipliers where they are able to do a much finer thing. But this toy problem and this toy tool just illustrates the overall importance of each stage, propellant mass, and the structure ratios and all that thing. Okay, so I will stop here. Thank you for watching.